Okay, let's dive in. Climate change.
Hmm.
It's this huge, huge challenge we're facing. And, it seems pretty clear now that just cutting emissions, probably not going to be enough.
Uh-huh. We're increasingly hearing about needing to actually pull CO2 out of the air, carbon dioxide removal, or CDR.
Exactly, CDR. And today we're going deep on one specific, maybe overlooked aspect,
Hmm.
the land use. How much space do these things actually need? We're basing this on a really interesting study called Area Demand Quantification for Energy System Integrated Negative Emissions based on carbon dioxide removal portfolios.
It's a critical question, isn't it? We talk a lot about if the tech works, how it works, but the where of it all, the physical footprint on the planet, that's crucial.
Yeah.
And this study, Area Demand Quantification for Energy System Integrated Negative Emissions based on carbon dioxide removal portfolios, really tries to pin that down.
So that's our mission today, really. We're going to unpack this study, figure out the key insights about land area for different CDR mixes, and importantly, the energy systems needed to power them.
Right, because it's not just the CDR tech itself, it's the whole system. Understanding this area demand helps us gauge, is this feasible? What are the knock-on effects environmentally?
hmm Are we just solving one problem by creating another?
That's the worry. This study helps us look at that more clearly. They used a pretty sophisticated method, linking a CDR model with an energy system model.
Giving us that bigger picture view.
Exactly. So the core issue this study tackles is hitting those climate targets 1.5 degrees, or even a tougher 1.0 degree target needs CDR, and lots of it.
A lot of it.
Yeah. But the land implications,
Yeah.
often kind of fuzzy or not directly compared, this study tries to fix that.
Okay, so to get a grip on this, they use two main ideas, gross area and net area. Let's break those down based on how this study defines them.
Sure. Gross area is basically the total space needed. So for wind turbines, it includes the space between them. For afforestation, it's the whole forest area. For energy crops, the entire field.
Got it. The total operational footprint,
Yeah.
sort of.
Pretty much. Then there's net area. This study defines that as the land that's actually, consumed or becomes basically unusable for biodiversity.
Ah, okay, so like the concrete base of a wind turbine, or the land completely covered by solar panels.
Exactly. Or those fields dedicated just to energy crops, which might not support much wildlife. That's the net area.
So a wind farm could have a huge gross area,
Yeah.
but a much smaller net area.
Right. And this study makes some key assumptions around this, like using biomass from genuinely sustainable sources, think forest leftovers, crop residues.
Stuff that's already there, basically.
Yeah. They assume that has no net area impact because the land's already doing something else.
But what about crops grown specifically for energy? The study looked at that too, right?
It did. And for those short rotation energy crops, the study is clear. Gross area equals net area. That land is basically fully occupied by the crop.
Okay. And the energy source is powering this stuff. How does the study handle their land use?
Good question. For wind power, they figure the net area is tiny, maybe 1% of the gross area, just the turbines themselves. Right. But solar PV, that's considered fully net area. The panels cover the land.
Makes sense.
And interestingly, for direct air capture, DC units, this study assumes they don't need much spacing based on how they're designed now, so their direct footprint is quite small.
Okay, so how did the researchers actually model all this? What was the machinery behind the analysis in this study?
They used something called the LUT CDR model. You can think of it as a way to weigh different CDR options based on what society might prefer, like do we prioritize low cost, low energy use, high permanence, that kind of thing.
So it reflects potential policy choices, in a way.
Sort of, yeah.
Yeah.
And they connected that model to another one, the LUT demand model, which
Yeah.
figures out the future energy system needed to support everything. It's this link that makes the study quite powerful.
Right, connecting the CDR demand to the energy supply and its footprint.
Exactly. And they ran this whole setup for two main climate goals.
The 1.5 degrees C target.
Yep, needing about 500 gigatons of CO2 removed by 2100 in their model.
And the really ambitious one.
The 1.0 degrees C target, that required a massive 1,750 gigatons of CDR by 2100 in these scenarios. Huge difference.
Wow, yeah. Almost 3.5 times more removal needed. And what kinds of CDR portfolios did they test within those targets?
They looked at 6 different strategies. One, heavily prioritizing biomass.
Okay.
Others focusing on low cost, low energy use. High security, meaning the CO2 stays locked away permanently.
Like geological storage.
Right. Then low area demand and high technology readiness, basically using tech that's more developed now.
And they did a specific test for biomass land use.
Yes. To really push the boundaries, they ran a case where all the biomass for CDR came just from dedicated energy crops to see the maximum potential land impact.
Okay, so the scenarios are set. What did the study find? What are the headline results for total area demand?
Well, for the 1.5-degree target, that biomass-heavy scenario, the one using only energy crops, it
Right.
really stood out.
In a bad way.
In terms of land use, yes. It had by far the highest total gross area demand, around 8.2 million square kilometers.
Wow.
And the net area demand was about 2.8 million square kilometers. And crucially, this study found most of that land use was directly for the CDR itself, the energy crops.
So not just the power plants, but the fields growing the fuel.
Exactly, which really highlights that potential competition for land.
Okay, how did the other non-biomass focused scenarios compare for 1.5 degrees C?
Much lower, and actually quite similar to each other, according to the study. Total gross area was around 2.7 to 2.8 million square kilometers.
Okay, significantly less.
And the net area was about half that of the biomass scenario, around 1.3 million square kilometers. In those cases, the study found it was mostly the energy system driving the land demand, not the CDR tech itself.
That's a really key finding from this study, isn't it? The source of the land demand shifts.
Absolutely. It tells you where the pressure points are.
So what about the more ambitious 1.0 degree target? Did things just scale up?
Generally, yes. The gross area demands went up for 1.0 degrees C, particularly for scenarios not specifically trying to minimize area.
Why was that?
Often due to more afforestation being needed in those models to hit the higher target. The biomass-only crop scenario. That went up to nearly 11 million square kilometers gross area.
Good grief.
Yeah. Net area around 2.9 million square kilometers for that one. Still huge.
But you mentioned one scenario was different, the one optimized for low area.
Right, the LAP scenario, they called it. It still increased for the 1.0 degrees target, but much less dramatically, up to about 3.7 million square kilometers gross area, a notable result in the study.
And the net area increase for 1.0 degrees C.
Interestingly, this study points out that for the non-biomass portfolios, the additional net area needed to go from 1.5 degrees C to 1.0 degrees C was actually relatively small.
So the gross area might balloon with things like forests, but the land actually paved over or intensively farmed doesn't increase quite as much for those tech-heavy paths.
That seems to be the implication from this research, yeah.
Okay, let's try and put these numbers in context. How do they stack up against, say, the total land area on Earth based on this study's figures?
Well, compared to the total global land area, roughly 130 million square kilometers, the percentages calculated in the study sound manageable, maybe?
Okay.
For 1.5 degrees C, the non-biomass options need about 1% of global land as net area. The biomass one, about 2.2%.
And for 1.0 degrees C?
Non-biomass stays under 1.5% net area, biomass still around 2.2%. So as a fraction of all land, it doesn't sound astronomical.
But I sense a but coming.
Well, yeah, the comparison gets much more stark when you look at cropland, as this study highlights.
Land we use for food.
Exactly. Global cropland is around 16 million square kilometers. Compared to that, the net area demand looks way more significant.
How significant?
For 1.5 degrees C, the non-biomass portfolios need a net area equivalent to about 8.5% of today's global cropland, according to this study. For 1.0 degrees C, that goes up to maybe 9 to 11.5%.
Okay, that's starting to sound like a real squeeze.
It is. But the biomass portfolios, much higher. Around 18% of global cropland needed for both the 1.5 degrees C and 1.0 degrees C targets in those scenarios.
Wow. Nearly a fifth of current global cropland potentially diverted to energy crops for CDR. That's a huge finding from this study.
It really is. It starkly highlights the potential conflict between large-scale biomass CDR and food security, or biodiversity on agricultural land.
Yeah.
The study even estimates that just the bio-based CDR options could eat up almost 10% of today's cropland by 2100 in those biomass-first scenarios.
Okay.
And that's before considering biomass for biochar.
Okay. This study also looked at specific area demand, right? Like land per ton of CO2 removed. Any key insights there?
Yeah, they did. And visually, the biomass portfolios really jump out with a high specific net area demand because of those energy crops.
Makes sense.
Afforestation, interestingly, drives up the gross area demand a lot in some scenarios. But according to the study's definitions, not so much the net area or the energy required. Sustainably managed forests are different.
And the technical solutions, DAC, et cetera. How do they look in this study?
Much smaller specific area demand, especially net area. This research strongly indicates that even when you account for the land needed for renewables to power them,
like wind farms or solar parks.
The overall land efficiency is significantly better than relying heavily on energy crops. That's a really central point in this study.
Okay, so if biomass CDR has these major land issues, how much biomass are we actually talking about needing in those scenarios? Did the study quantify that?
It did, and the numbers are pretty eye-watering, especially for the 1.0 degree target.
Lay it on us.
Okay, for 1.5 degrees C in 2050, the biomass-heavy portfolio needs somewhere between roughly 76 and 113 terawatt hours per year of biomass energy.
Which is a fair bit.
It is, but for the 1.0 degrees C target in 2050, that jumps massively. We're talking 1050 to 1560 terawatt hours per year.
Whoa. Over 10 times more.
Yeah. And looking out to 2100. For both targets, if you stick with those biomass prioritizing pathways, the study suggests you could need something like 4,300 to 6,300 terawatt hours per year.
That sounds enormous. How does that compare to, like, total sustainable potential?
This study points out it could be up to a fifth of the total estimated global sustainable biomass potential.
Just for CDR energy crops.
Just for that pathway, yeah. Again, not including biochar needs. It really raises questions about relying too heavily on that resource.
Did the study connect its findings to other research out there? Did it highlight any agreements or disagreements?
Yes, it did. It points out that many big climate models, integrated assessment models, or IAMs,
Right.
tend to lean heavily on BECCS bioenergy with carbon capture and storage to make the numbers work for deep decarbonization.
Because it's often cheaper in the models, right?
Often, yes, or fits the model structure well. But this study argues those models don't always grapple fully with the huge area demand and where all that biomass would actually come from.
And this study reinforces the potential downsides.
Definitely. It cites work suggesting large-scale energy crops can harm biodiversity more than they help the climate, and it flags potential conflicts with sustainable development goals like hunger, water use, biodiversity, health. It also notes its findings on DICCS area demand differ a bit from some other claims that suggest DICCS needs almost no land if not powered by solar.
What did this study conclude on that?
This study's integrated approach shows that while DICCS does need land for its energy supply, the total footprint is still way smaller than biomass CDR using energy crops. That comparative result seems pretty robust in their analysis.
Okay, so if we boil it all down,
Right.
what's the absolute key message from area demand quantification for energy system integrated negative emissions based on carbon dioxide removal portfolios?
I think the clearest takeaway is that from a land use perspective, technical CDR options like direct air capture seem to have a distinct advantage over biomass CDR that relies on growing dedicated energy crops.
Even with the energy footprint included.
Even with the land needed for renewables included, yes, that's what this integrated modeling suggests.
And this means hitting ambitious targets like 1.0 degrees C isn't necessarily blocked by land limits.
According to the study, it suggests it's not blocked by land availability and it's a big if we choose the right mix of CDR options, leaning more towards those land-efficient technical solutions.
But the study is also a strong warning against putting all our eggs in the biomass basket.
Absolutely. It highlights the serious potential downsides for food, water, biodiversity, conflicts with those broader sustainable development goals.
So the final word from area demand quantification for energy system integrated negative emissions based on carbon dioxide removal portfolios seems to be: we must consider area demand carefully when planning for large-scale CDR.
Exactly. It's a critical factor for a truly sustainable path forward. This study gives us a much clearer lens to view that through.
Which really leaves a question for you listening. Given these land use implications, which CDR approaches feel like the most viable and sustainable path forward? To really get into the details, we definitely recommend checking out the full study, Area Demand Quantification for Energy System Integrated Negative Emissions Based on Carbon Dioxide Removal Portfolios. It's a complex but vital piece of the climate puzzle.